Hi, good afternoon, everyone. So, welcome to my session. So, myself, Dr. Anil Kumar, a professor and HOD in the Department of Electronics and Communication Engineering, R.L.JALAPPA. So, in this today's session, let us discuss something about our quantization noise. And before moving on to our quantization noise, so I would like to say what exactly the term quantization stands for. And this quantization is very much essential in any of our communication techniques. And as well as, so we are very much familiar that, so we are moving from the analog to digital services, and any signal which is natural signal or any kind of signal which will be analog initially, and to communicate for the far distance, so we are going for the conversion of digital. And in this process, the quantization plays a very important role to convert that into any of my binary coding techniques. And after converting this into the binary or the digital one, so we wish to know the accuracy of this. And if the accuracy is good, the efficiency of the channel and the system will be always good. And for this process, so we need to estimate the quantization noise, or else just we can call this as our quantization error. And this quantization noise or the quantization error in the communication system, so it is nothing but the difference what we have estimated and what exactly the signal exists. That is what the term. So we call it as my quantization noise. So for this scenario, so we are going to represent the input message signal as the M condition. And in this input message signal, so usually it will be in the time domain condition. So we can call this as our M of t. And again, the output signal. So whatever we have estimated, so we are going to represent it as V. Now we have two variables, that is my M as well as V. M is my original signal and V is my output signal, whatever we have estimated. So for the representation, so I'm going to take this simple sine wave, and as well as, so it is represented as my input wave. And the second wave, so we have with respect to my quantized output. And usually this quantized output, which will be of the form of our staircase waveform. And in this staircase waveform, the process of converting this input M signal to V signal is called as my quantizer. And in this quantizer, we have two different types. So first one is uniform step size quantizer, and next is the non-uniform step size quantizer. Here, I'm going to make use of the term something called the non-uniform step size quantizer. So only you can observe here, so the step size, so whatever we are going to take care, which is of not uniform, it is linearly varying in accordance with my input message signal M. And as I described previously, the difference between M and V, that gives me the condition of my noise or else my error. And based on that, so this sawtooth waveform, the waveforms which are similar to my sawtooth waveform in the time domain, so we are going to represent something like this. And lesser the width between the peaks of my sawtooth waveform, so that gives me the error will be less. So just you can observe here. So here the distance between these two peaks are high. And again, this we are calling this as our error condition because of the overlapping scenario. And as we are taking care with respect to my error, M minus V, we have three different conditions to be taken care. That is, if the difference is less, the output will be positive and the output can be negative. And both M and V are same, that is the input signal as well as my estimated signals. So that will be same. That gives me the output as 0. So for this scenario, so we are going to simplify our discussion. So by considering the quantization input or the quantizer input, so we are taking it as my M condition. And after that, so we are taking the zero mean random variable. So we are taking this noise as my random variable, so with the M condition. And in this scenario, so we are going to take care that, so we have two substitute things for my random variable M as well as the V. and as well as the q we have, and the small q we are representing for the representation of my quantization error. So we are telling that the quantization error is nothing but the q is equals to m minus v. Similarly, so we can represent this as our, with respect to my random variable, the capital Q, which will be equals to m minus v scenario. And in this m, so we are assuming that the noise to be zero mean, and as well as the quantizer assume, so we are taking it for our discussion as our symmetric conditions there. And obviously, as we are assuming that the symmetric condition, so it is very much clear that, so we will also be a symmetric scenario there. So next, coming on to our next discussion, so we need to see that the continuous input signal. So input signal, so we are going to take care something with respect to my m, so which is going to vary from the plus m to my minus m condition there. And as it is varying between the plus m and the minus m condition, and we are assuming this as my uniform quantizer, and in this uniform the type of quantizer, so we have two different types. So one is my mid-rise quantizer, and next is my mid-thread quantizer. So for our discussion, so we are assuming it as my mid-rise quantizer type, and we are making use of my delta for the representation, and this delta, so we are taking it as my step size scenario. And in this step size scenario, to just to give the difference conditions there, so we are very much familiar that, so we have the condition, the higher voltage level, that is my VH minus VL, whatever we are having. And VH, usually it will be plus V max, and then, so we have VL scenario, so we have something with respect to my minus Vmax condition, as we are assuming that the input is swing between plus Vmax as well as my minus Vmax condition. And if you substitute these values, so we are going to get twice of its Vmax condition by number of levels, that we are taking it as my L scenario, total number of representation levels. If the number of levels are more, the error will be less, and more number of accuracy, and that leads to maximum efficiency of the system, whatever it is given there. So now we are limiting our quantization error to swing between plus delta by 2 and the minus delta by 2 conditions there. And again, it is very much clear that, so we should take care something with respect to our PDF condition there. So for this PDF, which stands for the probability density function. So this probability density function, so we need to take care that, which is varying between minus delta by 2 and as well as my plus delta by 2. So with that, having the value 1 by delta. So delta, as we have mentioned in our previous slide, so it is nothing but the number of levels and the Vmax conditions, whatever we are representing. And apart from these values, minus delta by 2 and plus delta by 2, it will be 0 otherwise condition. The PDF, so we are going to take care with respect to FQ of my Q condition, and we got this FQ of Q based on the basic definition of our random variable. So with this scenario, so I can tell the variance, which will be equals to the varying with the upper limit of plus delta by 2 and minus delta by 2 with the q square, and the function, the PDF function with respect to q, which is nothing but the expectation of my q square. And if we substitute this FQ of Q as my 1 by delta and keeping the limits as it is my plus delta by 2 and minus delta by 2, after simplification, so we are going to get delta square by 12. And this delta square by 12 is the variance, whatever we have considered with respect to my random variable, or as the PDF probability density function for our given random variable there. Now let us see how to discuss, or else how to define this value of L. And that gives me L is equal to 2 to the power of R, and R denotes the number of bits, whatever we are representing. For example, so if we substitute R is equals to 1, the L will be equals to 2. If we substitute R is equals to 2, the L will be 4. And if we substitute R is equals to 3, the L value that will be equals to 8. And it is just a simple binary calculations. So whatever we are having there. And we are substituting the same value of L, which is nothing but 2 to the power of R. And so my variance, whatever we have defined with respect to my random variable, which is going to change to delta square by 12. and with the substitution, delta is equals to twice of V max or M max value by 2R with the simplification. So we are going to get 1/3 of my square of its maximum frequency, maximum voltage value, that divides 1/2 to the power of minus 2 to the power of R. R else take to the numerator. So this is my variance equation. So whatever we are getting there. And finally, and if we are going to express in terms of my SNR, which stands for signal to noise ratio, it is the power that divides the variance condition, and keeping this P as it is. So then the final equation, the signal to noise ratio at the output, so we are going to get it as thrice the power divides the square of its maximum voltage value to the power of 2R condition. And assuming that the main signal as my sinusoidal signal, so which implies that the P value, so P value will be equals to AM square by 2. And substituting in the previous equation, so we are going to get the final equation as 1.5 times RL something with respect to 3/2 times of 2 to the power of 2R. And this is for the final output of my SNR value. And if we wish to express that SNR in terms of TB, as per the basic definition, again it is clear that, so if we express 10 log of this SNR, so that gives me the value of 10 log of SNR of the output condition. So if I substitute the SNR value 3/2 times of 2 to the power of 2R condition as 1.5 times of 2 to the power of 2R condition, and making use of our simple logarithmic formula, so log of x to the power of y, so it gives me the value of y into the log of the 2 condition. So then the final equation in terms of the dB, that is my decibels, so we are going to get 1.8 times of my 6 times of the R, and where R defines me the number of bit levels whatever we are going to consider. So if we take R is equals to 1, which gives me the SNR output in terms of my 6 plus 1.8, that gives me 7.8. If R is equals to 2, that gives me 12 plus 1.8, that is 13.8 condition. If R is equals to 3 condition, so that gives me 6 into 3 and again plus 1.8. Similarly, so if we are going to change the number of bits, whatever we are representing there, this is the summary of the representation of the R, whatever we are giving there. So finally, it gives me the condition. If I substitute R is equals to 5, 6 into 5, that is 30, 30 plus 1.8, that gives me 31.8. And in the first column, so I have represented something with respect to your representation of the L value, that is 2 to the power of 5, that gives me 32 levels. And as the number of levels are increasing, you can see that the SNR values are also getting better there. So this is the final proof that if the number of levels are increased, that we are going to get the better SNR value in terms of dB. So even if you go for the R value is equals to 10, so then we are going to get the better value. So I'm concluding this session. So with respect to the SNR in terms of dB for our quantization error, which implies that as the number of bits are increasing, which gives me the better SNR value. And with this scenario, let us conclude that if the number of bits are high, so which implies, so we will be having the better SNR value, and which implies the noise will be reduced. And if the noise is reduced, so whatever we have expressed, so with respect to the scenario of the quantization, so that will be better. So hence, I would like to say that to have the better accuracy in the conversion of analog to digital conditions there in terms of my quantization. So again, it is clear that, so we are going to tell number of bits are increased, so that if the number of bits are increased, the step size will be more accurate. And if we have the more accurate level, so easily we can say that, so we will be dealing with respect to an ideal system. And thank you.